Finishing up chapter 8, let's start off with a question for you guys. We have a car that is circling around some point, moving at a constant speed. So we can draw a little picture. Let's assume it's going this way, perhaps. Moving at a constant speed. We want to know is the car an inertial reference frame? So pause the video, think this over, and we'll talk about it in a second. The answer is no. An inertial reference frame, and this is a really tricky kind of idea, or at least it sounds tricky, but basically an inertial reference frame is a reference frame that is not accelerating. Okay, so the acceleration of the frame has to be 0. Now here, our car is going at a constant speed, so velocity as a vector has two parts to it. Okay, any vector does. It has the magnitude and the direction. And so we're going to talk a lot about this during this lecture. And so in this case here, the magnitude is staying the same. However, the direction is changing. When the car is over here, its velocity will be there. When the car is over here, its velocity will be like that, and so on and so forth. And so the direction is constantly changing, so the car will be accelerating, okay, but it's not speeding up or slowing down. It's just changing its direction. So we're going to talk more about this. But what the book does now is it talks about inertial reference frames. So I kind of wanted to go over just what they are in relation to what's called a fictitious force. And so let's assume that we're in a car that is slowing down. So here's the picture. You're in some car and it's slowing down. If you're in the reference frame of the car, okay, so you feel as if there's some force that's throwing you into the windshield. All right, and this force, we call this a fictitious force. It's fictitious because there's no real agent. So the book says agent. What that means is just something that causes the force. There is nothing causing this force. If you're sitting next to this person in the car and you see them lean forward, all right, there's nothing pushing them forward. And so that's why it's fictitious. They're not real. Fictitious forces basically come up when you're in a non-inertial reference frame. So here the car is accelerating. So its acceleration is not 0. So it's a non-inertial reference frame. If you look at this from the outside, okay, what's happening is the person in the car are moving to the right. Okay, they're moving to the right, the velocity v here. And as the car slows down, the person has a tendency to continue forward with this velocity. And that's what makes them lean forward. And then, and basically, to sum this stuff up kind of, in this class, we're almost always just going to be concerned with this picture here. Okay. However, this is a pretty tricky topic, so it's kind of good to bring it up. But we won't deal too much with fictitious forces. Some books don't even mention them, but just realize a couple of things. So first of all, generally, if we are in a non-inertial reference frame like that car, we will feel a fictitious force. And generally, usually, the acceleration in that situation is oppositely directed from the fictitious force we feel. So in this case here, all right, the acceleration is backwards to the left, and the fictitious force we feel is forwards to the right. Okay, so that's the decelerating car. In an accelerating car, all right, if you push down the gas, your acceleration is forward, but you get pushed back into the seat as if you're getting pushed backwards. All right, and we'll show in a second how that works for a car that is turning. But basically, I think this can be a really useful idea. As a concept, this is very confusing. This is what makes some of this stuff that we're doing right now very hard for people, is that their intuition is sort of opposite of what the acceleration is. All right, but I think if you remember this, it can be handy and hopefully be helpful. So if we look back at that car moving in a circle, so the car is moving this way with some velocity, we know that its acceleration is this way. But if you're in the car, if you're this person right here, you have this tendency to want to keep going. So as the car turns this way, you're going to run into this side of the car. Okay, so again, you're going to feel this fictitious force oppositely of what the acceleration is. So as a general rule, if you're accelerating, you feel it, okay? And you're going to sort of be pushed in the direction that's opposite of the real acceleration. You know, for instance, if you're on a train going at a constant speed, you don't really feel anything, okay? If you ever had a situation where you're on a train and you see the one next to you, you can't tell which one's moving, that's because you're not accelerating. You feel accelerations. You generally don't feel it when you're going at a constant speed. So to look a little bit more, let's look at a case like here. So here we have initial and a final velocity, these two yellow vectors. So here's my initial right here, and here's my final. I want to know is if these are my initial and final vectors, which one on the right gives me the correct direction of the average acceleration during this time interval. So pause, think this over, and we'll talk about it. All right, hopefully you got this one here, B. Let's look at this. So if the question is, average acceleration is change in velocity over change in time. All right, and we can think about these velocity vectors as being vectors, right? And so I want to know is what will make this initial vector turn into that final vector. And if you look at it geometrically, to start with VI and to get to V final, what I do is, and we can think about it as adding the vectors head to tail. So this is my first vector, all right? If I add it head to tail, it has to be delta V like this, okay? That's going to be the vector that's added to this one that makes V final. And so basically it'll be directed straight down like we were talking about. The other way to kind of think about this is to break these two velocity vectors into their x and y components. So you look here, the x component isn't touched at all, and so this delta V should not be in the x direction at all because the velocity there stays the same. And what happens is the velocity is initially going upward in the y direction and afterwards going down in the y direction, and so that's why this thing has to be downwards. Okay, it's canceling out this positive and then making a negative in the downwards direction. And this is hopefully a little illustrative in just understanding the acceleration in uniform circular motion. If I take that car, for instance, moving in a circle and pick two different points, here my velocity initial is like that, my velocity final is like that, and it's basically the mirror image we just had, which tells us that delta V should be in towards the center. And what we can do is, so this is the average acceleration, and to make it more like an instantaneous acceleration, we can basically bring these radii in closer together. And if we look at here with the VI and the V final, we get the same thing, delta V, and you can imagine as you get that R, even those radiuses closer and closer together, you get basically an instantaneous acceleration. But the point is that the delta V is in towards the center of the circle. All right, so you can kind of think about it, you know, imagine if this was a planet right here. All right, so a planet that was rotating. Okay, so the planet wants to keep going off this way here, and so you have to pull the planet inwards, okay, in order to change its direction of velocity like over here. A lot of ways to think about it, but hopefully one of them makes sense to you. And so the key is that the centripetal acceleration in uniform circular motion is towards the center of the circular path. And so here's the way the book breaks it down. So what they do is they make the radius, the r-axis, which is like the radial axis, and the tangential axis. And so for uniform circular motion, your acceleration is in towards the center, all right, and there is no acceleration in the tangential section. We'll talk more about that in a little bit. And here's v squared over r as a centripetal acceleration, and you can use what we call the viewer equation as sort of a little shortcut that translates from our linear value of velocity to the angular value of velocity through the radius, and that's also this equation right over here. This is a picture of a polar bear, and moving on to rotational motion. So we're talking about non-uniform circular motion, and I always like, whenever I bring up rotation, we're going to talk about rotational motion a couple times this semester just to back up and remember what we were doing before. So with rotational motion, we found that our old-fashioned variables came up short. And what I mean by that is, suppose this disk here is rotating, and we pick 5 points on this disk. We had to pick 5 random points. If we watch their motion, okay, it's going to be very different, the inward dot towards the outward dot. Okay, my circles are really bad here, but basically every point goes a different distance in terms of meters. So our old-fashioned values, position, velocity and acceleration, where this is measured in meters, meters per second, and meters per second squared, are going to come up short here because every point on the circle, all right, goes a different distance, will have a different velocity, etc., etc. And so what we do to combat this is we change our units. So before we were dealing with meters, now we deal with angle in radians. Okay, so before we had position in meters, now our position is measured in radians. And if you look here, or if I pick 2 points on the circle, all right, they do travel different distances, but they travel the same angle. And so it makes it much easier to describe the rotation of something in terms of the angle instead of meters. And so it's generally measured in radians, and the units are positive if counterclockwise, negative if clockwise. Is generally clockwise how we do that. But the point is, all points on the object have the same angular displacement, which is why we do this in the first place. And so then we find, as we go through and do this stuff, so we used to have position in meters, now position is in radians, and it's a theta. Our linear velocity v was in meters per second. Now our angular velocity is radians per second. And then finally, we had linear acceleration. Now we have angular acceleration, which is radians per second squared. So technically, you can describe everything with either which one you want to, all right? But it's just easier to describe rotating objects in terms of these guys here. And then we use these. These are our constant acceleration kinematics equations. And they're the same ones we used before with just different letters in there, kind of like it's a different language or something, but it's the same concept to use these. And then real quick, what we want to do sometimes is convert between our linear values and our angular values. And so the first equation we have is just the definition of radians. Sometime long ago, we all learned this in a math class. Okay, S equals R times theta. It's how you relate the arc length here to the radius of your motion with your angle theta. And so here, if I was to pick this point here, you notice this would be a smaller radius, and so this arc length is smaller than this big one over here. All right, and that's because arc length equals R times theta. If we were to take the extreme case, so arc length is radius, let's suppose that our thing goes 2 pi, a distance of 2 pi, arc length then is 2 pi r. And so if I do that to go all around 2 pi r, okay, an angle of 2 pi, that means my arc length, which when it goes all the way around, we call it circumference, is 2 pi r. So that's where this definition comes from, that way there. But again, it's a way to convert meters into angle and vice versa. And the point is, bigger radius, more arc length. And then we can take this and divide, say, by time on each side. So here I have arc length divided by time, which is a velocity, and then theta divided by time, which is an angular velocity. And we get this equation, the viewer equation. Again, it's just a way to convert linear velocity to angular velocity. And you can do the same thing and get something that looks kind of like this here, which is a way to convert between tangential acceleration and angular acceleration. This will be really important. We'll talk about this a lot in this lecture. But these are the ways to convert between the angular values and our linear values. And so the final thing, when we're doing with non-uniform circular motion, okay, you're going to have two kinds of acceleration. And so we want to talk about these accelerations a little bit. And this is going to go along with what we were talking about before. When you have a vector, okay, the vector has two quantities. It has its magnitude and it has its direction. Okay, centripetal acceleration is a change in the direction. And so if you have some kind of circular motion, you're always going to have centripetal acceleration. It points towards the axis of rotation. So here it's inwards. Okay, in the book we'll call this A sub r. You can kind of do either. It's sort of synonymous. Now the tangential acceleration comes if the disk is speeding up or slowing down. And that's a change in the magnitude of the velocity. And so that's if its speed is changing. You can have both of them depending on what's going on, but we'll talk more about this later. But sometimes you can have just centripetal acceleration. And so here's the book's definition of this. Again, we have this equation of how to relate tangential acceleration to the angular acceleration. And then here's how we write our centripetal acceleration in terms of v squared over r omega squared times r. And in general, there will be two cases of rotational motion that we'll be dealing with, and this is true for everybody. So there are basically two kinds of, the first kind is object is rotating with a constant angular speed. Okay, in that case, the object has centripetal acceleration. Remember, that's the one that changes if your direction changes. If you're rotating, your direction's always changing. The object has no tangential acceleration because you're going at a constant speed. And so tangential acceleration is always if your speed is changing. And then the object has no angular acceleration. So this equation here is key. Tangential acceleration and angular acceleration are really the same thing, just in different units. Okay, so tangential acceleration and angular describe the exact same thing, which is the tangential is in meters per second squared and the angular is in radians per second squared, and you convert from one to the other by multiplying by the radius. And so if there's one, there has to be the other. If there's not one, there can't be the other. And the other case is object is rotating and its angular speed is changing. This is non-uniform circular motion. And this is the object has centripetal acceleration, it has tangential acceleration, then of course it's going to have angular acceleration because those always come together. So let's look at an example of how something like this might be a problem, or how we might do a problem with these topics. So an object is rotating in a circle here in this picture, and the velocity at this frozen moment in time, it's like a snapshot picture, is to the left. As it is rotating, its speed is increasing. What direction is its acceleration vector pointing at this moment? You got a whole bunch of choices, so pause, think about this, and we'll talk about it in a second. All right, hopefully you got that the acceleration vector is d. So first of all, when we talk about acceleration vector and we don't put angular in front of it, we're talking about the linear acceleration a. And so at this point, there's two components of the acceleration. So this would be non-uniform circular motion. All right, and so you'd have a centripetal acceleration pointing into the center of c. All right, and also because your speed is increasing, you're going to have tangential acceleration this way. And so if I take c and d, well, together they're going to have a vector somewhere in the d direction. All right, we'll talk much more about this coming up.